Hello everyone and welcome to today's live broadcast, Hardware Architecture and its Use in Facilitating Collaborative Development and Dissemination of Microfluidic Experiments, presented by Dr. Carlo Quinonez, Director of Research at Fathom. I'm Julie Simroth of LabRoots and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots, the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. For questions not answered today, we will follow up with participants via email. Also, please notice that you will be viewing the presentation in the slide window. To enlarge the window, just click on the icon located on the lower right of the screen. If you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window or use the Q&A button to let us know that you're having a problem. This is an educational webinar and thus offers free continuing education credits. After the webinar is over, please click on the CE button located in the bottom left-hand corner of your webpage and follow the process of obtaining your credits. Please join me in welcoming Dr. Quinonez. I will now turn the presentation over to him.
Hi everyone, my name is Carlo and I'm, as Tracy mentioned, the Director of Research at Fathom, and the talk today is open source hardware and scientific discovery. I wanted to start a little bit about Fathom and our core values. Fathom takes a lot of pride in our ability to design, the precision that we put into our products, and also the capabilities that we have to build unique designs. To get things started, I'd show you guys a great video that we put together. I love that video. So Fathom started in 2008 as a simple reseller for a company called Stratasys at the time, Object Studio at the time, sorry. And over the years, we've expanded services to offer service bureau work, so turnkey manufacturing for people, value add design services to help people improve designs and optimize them for additive manufacturing, contract manufacturing, and most recently, we added a research component for companies interested in exploring the additive manufacturing space. We have offices in Seattle and Oakland, as well as full-time staff in China for lower volume, kind of mid-volume production, and probably most relevant, contracted consulting services for individuals and organizations that are interested in exploring how 3D printing can affect their businesses. And that's where I fit in. So as Director of Research, I lead those contract research projects for other companies. Prior to joining Fathom, though, I was a postdoctoral researcher, and I'll talk a little bit more about that background, but I just wanted to mention some of the professional affiliations that are relevant to this presentation. I'm part of the technical advisory board for LimForge, which is a nonprofit group developing designs, parametric designs for 3D printable prosthetic devices, prosthetic arms. I'm also a member of the Autodesk's customer advisory board for their Fusion 360 CAD software. And probably most interesting to you guys is an editorial board member of the Hardware X. And that's a free and open scientific, a journal devoted to free and open scientific hardware, published by Elsevier. It's open access, which means anyone can get access for free to the journals. And one of the requirements for publication is that all designs have to be submitted in an open source hardware license. Just started last year, but pretty exciting developments that even the somewhat stuffy industry of scientific publishing is getting on this open source bandwagon. But it's more than a bandwagon. So we'll start this talk. I'll walk you guys through a little bit of this journey of how I got to today. I promise it's going to be fast. So I love this quote. Science and technology have progressed to the point to where what we build is only constrained by the limits of our imagination. And it's inspirational in some ways. And by the end of this presentation, I hope this quote will mean something different to you than it does right now. So back in 2009, I started working with in a cell biology lab at UCSD, and we used microscopes to study cells, right? If you're keeping cells alive on the microscope, you'll need to put them in an incubator. And this is the first design I made for a 3D printed stage top incubator oven. It really closely parallels the designs of commercially available incubators. Some of the features that I was able to bring in because of 3D printing is these manifolds. Highlighted in green there is a little tube that's printed as part of the housing. That's one of the nice capabilities that 3D printing gives us ability, is to print these kind of long passageways inside of parts. It used a metal aluminum tub to kind of provide some thermal stability and distribute the heat around. And there was these two Kapton thin film heaters attached to the underside of that aluminum block, and that's what heated up the sample chamber. The next iteration, I stopped and asked myself, why did I build a box? Right? I have the technology that lets me build any shape I want, but I built a box. And that's when I began to realize how constraining, that everything that you've been exposed to in this world has been manufactured conventionally. And that colors our expectations, our assumptions, our approach to designing hardware. Everything you've seen since you were a child was in a box. So naturally, when you start a new product, you put it in a box. Questioning those kinds of assumptions is what we do best. So some other nice features that this design had was a sealed chamber. So we used O-rings to provide an airtight seal between the sample environment and the outside environment. That gives us the capability to capture that effluent gas and make measurements on it. At this early stage, I didn't want to go too far into that capability, but there was one feature that we did need, and that's a rotometer, which is a flow meter, right? So this design is incorporated directly into the 3D printed housing, and all that it is a tapered tube with a ball floating in the middle of it. Normally, rotometers cost over $100 for their precision manufactured, but all we needed was a simple go, no go. Is there air flowing through there? If there's no air flowing through there, the ball's at the bottom of the tube. If there's too much, it's all the way at the top. And we designed it so that if the ball's floating in the middle, you have enough air. This is a great example of the kind of small user features that you can put into a design easily and almost no incremental additional costs with 3D printing. And the last iteration I did in my postdoc was much more sophisticated and built off that. Once I broke free of the box, the design begins to follow what's happening underneath. Like the form really is following the underlying functionality of these parts. One of the features we had in here was we broke up that aluminum block into two separate pieces. So now we could control the amount of water that goes into the humidification process. So how hot that is controls the level of humidity, and a separate zone for controlling the temperature of the cells. We also managed to fit in some commercially available off-the-shelf miniature fans. These are fans that were used in devices like laptops, I don't know about cell phones, but any small electronics that needed cooling. We just used them in this design. We 3D printed out the mounts. Actually, the mounts were incorporated into the chamber housing. So there's one big 3D printed part that has a lot of different functions, attachment points, and all of that is easy to do because it's all printed out in one part. That aggregation of functions, combining all these different functionalities into one part, is really powerful, but your design has to start supporting that, and that's a little different. So as I mentioned, this had two separate heating zones, a block in the front for the temperature zones controlled by its own thin film heaters, and then the zone in the back for controlling the amount of humidification. But of course, microfluidics requires a lot more than just incubation. And microfluidics is basically the automating of biology experiments, right? Because all biology experiments are just moving liquids around from one container to another container, right? Stirring it, doing something in that sample, then moving it into another container, right? And sadly, that's what you can ultimately break down a biology experiment into a series of liquid handling steps. And this is well known. And taken advantage of in other ways. The big problem that we're trying to address with this automation, either microfluidics or conventional like fluid handling robotics, is tackling systems like this. And so this is a chart of the cell signaling pathways of macrophages, right? So this is basically the circuit that controls your immune system, right? You don't have to read it, just appreciate the complexity of it, right? Each box is a single enzyme. All the connections represent the enzymes that it's connected to biochemically. And this one system exists inside the cell with other systems for controlling cell cycle, cell death, differentiation, all the other cell pathways all coexist in the same spot. So you have crosstalk between them. And that leads to an enormous challenge, right? So in order to really probe this, the amount of data you need is staggering. You need to do hundreds of thousands of replications, and if you're doing that many, it becomes a challenge to ensure that the data at the end is comparable to the data at the beginning of this experimental run. In many labs, what they've done is use microfluidics, and microfluidics is a technique where you basically miniaturize and you translate that big liquid handling challenge into a single small device. All the little tubes you see there run pneumatic valves on the chip. And so just to give you a sense, this is the device I worked on. These blue areas are where the flow is showing in this little graph. I have a video. I'll make this a lot more clear what's going on. But by basically opening and closing valves, you can change where the flow is moving. And the whole point of this little small sequence of operations is to get cells seated into these 6 vertical chambers in the middle of the device. This video will explain a lot more. So right now, those red boxes indicate everything's closed. Now one valve just opened, and now you see the cells flowing through the chamber. Shortly, another series of valves will open up, and the flow is diverted. Now it flows around the chambers. So the chambers are now seated with cells reproducibly, and there's 6 of them on this one device. And that's essentially microfluidics, just opening and closing valves. They just happen to be very, very small valves. The size of these valves is about 200 microns across. Now, that's what we did in our lab, and that was nowhere close to the state of the art. This is a paper that was state of the art at the time. They've, in this paper shown, they've used microfluidics to design a device capable of addressing 96 individual chambers and controlling the media composition of that, completely automated. So just this is that little box that just highlighted is one of those chambers that is being controlled. So watch this video, right? So now you see they're using a colored dye solution and pumping it into the different chambers. And they can control that on a chamber-by-chamber basis, including mixing of 2 different media compositions and dynamically mixing that across all 96 chambers, right? And this is like amazingly powerful technology that's available. And in all the publications that you've seen about this, they probably don't talk about the hardware. Everything else that you need in order to make that little device, right? Because whenever they show you pictures of devices, they usually put next to a quarter or a dime. Some size scale reference showing you how small it is, convenient leaving inside all the rest of the equipment. I mean, you really got to think of it as an entire stack, right? You're running your experiments on this microfluidic device. That means you need control software. Right now, it's all developed by like the individual scientists, labs, or groups. The microfluidic hardware, the series of valves, the incubation, all the tuning, the plumbing to connect everything together, and that's all scientists developed. And then finally, that microfluidic cartridge itself, the circuit board in a sense, and that's all developed custom as well. And so what you end up is with an entirely custom stack that's difficult to reproduce and scale. When I started this project in 2009, my vision was to make it a lot more robust and easier. My goal was to make it so that a work study student working in the labs could actually run microfluidic experiments. And so in this vision, we're relying heavily on community developed or open source software. But I really want to emphasize, I say community developed because I want to emphasize that it's the users of this technology who are the ones that are developing it. In the microfluidic hardware, all the equipment you need to run it, and the microfluidic cartridges to make those modular so that they can be assembled out of parts. And so a quick overview, we have the software running on a computer, we have some 3D printed hardware and electronics that run the valves and the heaters, and then of course the microscope and incubator. We talked a little bit about the incubator, I'll talk more about that in a second. So there's an incubator control module that has a bunch of 40-watt, full bridge power drivers, serial control. Basically, it runs the electronics of the incubator and the substage heaters. We have the pneumatic control module. This runs the pneumatic valves. So essentially, the microfluidic device has air-piloted valves, right? So they're valves that need an air pressure source to operate. And this pneumatic control module is what provides that source in a way that's easily controlled from your computer. The Safe Shop incubator, and when I designed this, I made sure to start with templates, right? So the goal of this was to allow for customization. I wanted to make it easy to customize. So I started first by building a blank slate, a blank lid for that incubation chamber to make it easy to make customized versions of it. The incubator is very highly instrumented. Like it has 3 onboard temperature sensors, and then we do remote sensing of the temperature of the actual heating elements for a total of 5 readings from a device the size of 5 temperature readings from something the size of a book. And normally I'd collect data over the course of a single run, so a few hours. And that data always was solid. Straight lines is what you'd expect for something that's not changing, like temperature, at least not changing during the course of the experiment. But one day I accidentally collected data from several days. I tried to turn off the data collection and saw some really interesting transients in the data that corresponded to, I didn't know what actually. I was a little surprised. And so I did some follow-up work on this. And so this is the first poll that I'd like to do. So if you guys want to take a moment to answer. All right, curious to see what you guys say. That what it turned out to be was the door to the room being left open. Right, I had to put a web camera in the room, and sure enough, some days some people would open the door and leave it open, right? Put the door stop down, and that was the cause of these power fluctuations in the heater. And that's when I had that other realization that, wow, here's this hardware built off of Arduinos, very simple 16-bit microcontrollers, and I can detect whether or not the door to the room is open. There's this generally held belief that, this is funny, when you get scientists talking, confident or confide in you, that sometimes cells act differently in different labs. I don't really believe that at all, right? If that's true, then we should just go home with scientists, like if it's not predictable. I think that the deeper truth there is that cells act differently because environments are different in different labs in ways that we don't appreciate. And having richer data sources to mine, to be able to go back and look for other explanations for variability could be a very powerful tool. Anyway, so these designs support conventional, like Petri dish-based experiments, microfluidic, and cartridges are supported in this hardware platform. The cartridges themselves have features such as on-chip reservoirs. So rather than having to load the samples up into a separate process, right? And that's an in-depth. It's a pain in the butt to run microfluidic experiments. Here we have on-chip reservoirs and these little those little gaskets on top of the device interlock with the lid to provide an all-at-once interface. Another capability here is a single-layer valve. So normally valves in microfluidic devices require 2 separate layers of PDMS that have to be bonded and aligned, which is a challenge. In this case, we figured out how to make single-layer valves. Other innovations are this chip to cartridge to world interface. So normally, as I mentioned with microfluidic devices, when you have a microfluidic device like this, see these little tubes running out of the in the picture to the left. Each one of those has to be plugged into the device manually by the experimenter when we're setting it up, which is a real pain. This allows us to hook up all the connections at once, just like you would on a computer. We also have ports that allow replenishment or emptying of the sampling of the reservoirs. This is what's shown on the right. Those devices are, the microfluidic cartridges are made from 3D printed molds. Also developed a 3D printable, like the hardware jig and fixture that you need in order to do the molding of the devices on your desktop reliably. 3D printed hardware devices for bonding the silicone rubber device to the plate of glass. Because normally you bond it using a heavy weight to hold the device down to the glass. In this case, we had to use air pressure. There's also a lot of modularity and opportunities to customize the functionality and design. So on the left and right, I'm just showing you the negative spaces inside the pressure regulators. The one on the left has 8 outputs, and you can control the pressure from the software, but it takes like a minute for the device to adjust to a new set point pressure. The one on the right has fewer outputs, only has 6 outputs, but has much faster dynamic response. So that one can adjust the new PSI in under 5 seconds. And this is a great example of how using a standard piece of hardware, the electronics, you can have a very divergent functionality by swapping out the 3D printed portion and changing out the firmware, right? 2 things that are very easy to do. The designs for the device themselves also are these feature-based components, and the best way to show you that is this video. And so this is a plugin I've written for Fusion 360 for doing microfluidic devices. So that once you start the plugin, you just lay out the fluid pathways, the center lines of the pathways. And so we're just going to make a very simple T-junction. And that green box is the extents, the max build area of the device. So we can add valves. And so here we're just going to make a device where I can select media or some solution coming in from the one side of the T versus the other. So we need valves to control that flow. We can switch one valve on, one valve off. This gives us a reservoir on the output side, so we can collect the sample. And now we're adding 2 reservoirs for the 2 arms of the T. And then at the end, once you're happy with the design, you guess, compile it, as it were, and you make the molds. Using this tool, I mean, we can, I've had other groups that can iterate on designs on a day-to-day basis. So they start a design on Monday morning, and by Tuesday afternoon, they're running experiments on cast devices of that new design. The capability to iterate quickly and reproducibly is unparalleled. Another concern is, of course, how do you build this, right? These current devices literally take a PhD to run. Scalability, accessibility is a key feature. And so this video just shows you, that's Joe. He used to be one of the shop workers at the Scripps Institute of Oceanography Machine Shop. You know, he'd never seen any of this hardware before. We gave him instructions and all the hardware, and he was able to assemble another working device in about 2 hours. Here's showing that the microfluidic device and a 3D printed interface, and we do the connections all at once. And finally, the control software. Right? So this is based off Micromanager, which is open source software developed at UCSF in Professor Vale's lab. It's basically a platform for automating any microscope. We have plugins in it for controlling the finest hardware, and what you see here is how you control the flow paths, right? I mean, basically, you know, the valves can be in state, you know, either flowing media through or not flowing the media, applying flow from the adjunct reservoirs, right? You see how the flow paths switch. You can also control the set points. And on the right, you see the, in the bottom right, the control manifolds, you see the pressure set points and the valve states responding in real time. You know, this is open source software. You know, and this was where the postdoc project ended. You know, fortunately, recently I've had a chance to revisit these projects and keep pushing forward on it. So remember, this is where we left off. This was the last iteration I made at UCSD. It was, you know, fully 3D printed, lots of advanced capabilities. And so this is where I want to ask the second poll. What would you do next, right? Where would you take this design? Now, very interested to see the results that, I want to go back to this quote, right? The reason I actually find this quote depressing, if you're a technology CTO, right, at Intel, of course, you're very proud of the technology. But as an engineer and scientist, it's saying that our imagination is the weak link. It's not technology. We can build things that we can't even imagine yet. And our imagination is that what's holding us back. And I realized that over a period of time, many, many years, working with this. So I took it upon myself to get rid of the metal, right? Can we make an incubator that didn't rely on metal? And so the reason we have metal in incubators is that we're relying on the passive thermal conductivity. Remember, in these designs, you know, there's this relatively high concentrated heat source, that thin film heater, and we want to spread that heat evenly around and control like temperature fluctuations. I'm sorry, and control temperature fluctuations. And so there's lots of good reasons to leave metal in there. The one thing I don't like about metal is that you can't 3D print it out, but not affordably yet. We're working on that though. But you know, as a design exercise, can we get rid of metal? And so I started focusing on that. And so this is my first stab at that. It uses a blower there to heat air, to push air through this really complex ductwork, and those light green vertical kind of fins are heaters. And so these ducts distribute the heated air around the surface. This is a proof of concept, right? Am I crazy? Can you actually build an oven without using metal? And it actually worked surprisingly well. You know, some of the things I realized or noticed was that even though the plastic was hot, it felt much cooler to the touch, and it was also very, very responsive to changes in temperature, right? So if you set a new set point, it responded very quickly. This led to my next project, which was taking this one step further. This is Project Pyra. It's a fully 3D printed oven uses an FDM technology, so the plastic resin is actually approved for food contact. The fan underneath is 3D printed out. Those green elements are still normal heaters, still electrical heat. But aside from that, the rest of the device is 3D printed. So there's 300 watts of total heaters in the base that can heat the inner chamber up to 200 degrees Celsius. The plastic is rated for up to 280 actually. There's these heat sinks that are integrated directly into the chamber walls to distribute heat, and the heated air flows up into the device through these passageways. They're generated so that the cross-sectional area remains constant the whole way through. And some of the challenges of this, and for me, this was the point of this. I don't expect people to use this design, but how do I learn how to build these kind of convective ducts and heat sinks in different orientations? In the end, we printed one out, it worked, and we actually cooked some steak with it. And people ask me what it tasted like. I'd like to say it tastes like victory, because even my boss didn't think it would work. That's research. I invite you to go to our website and watch videos about Project Pyro. You can also go to YouTube and just Google Project Pyro to learn more about it. One of the current research projects we have is pushing this technology the next step forward, Project Crucible. It kind of builds off of what we learned in Pyro to develop an incubator for doing xenobiology or extremophile biology, depending on your specialty. But the incubator is capable of creating a near vacuum, right? So we had to figure out how to do airtight FDM printing, as well as going down to near minus 80 degrees Celsius, and controlling the light levels inside. So this top, the fins on the top are actually a heat sink for a 30-watt LED to illuminate the interior content. The goal for this is the partner in this is using it to explore how to do synthetic biology to optimize organisms to grow on Mars. And to simulate Martian environment, near vacuum, fluctuating light levels, and as low as minus 90 Celsius. And so those were the design specs. We figured out how to 3D print insulation, or how to optimize 3D printing infill for insulated properties, novel slicers in order to get it to print out airtight parts. And ultimately, the design has 9 3D printed pieces, and the costs for everything except the hardware. So what's not shown in the picture, of course, is the huge chiller, the cryogenic chiller. And it was like 30 grand, and then the vacuum pump, another 2 grand. The cost of 3D printing out all the components is about 2.5 grand. So out the door, you're looking at 50 grand to get this whole thing up and running. A conventionally manufactured incubator that can do conditions on Mars, and there's 2 of them on this planet, one here in the US and one in Germany, or Europe, I'm sorry, costs about $250,000. Totally bespoke engineering, right? Maintenance and scalability is hampered by the cost and the manufacturing approaches. 3D printing kind of opens that up. So I wanted to show you a video about what I am inspired by and what I'd like to figure out how to bring to biology. This is shouldn't be any audio.
Produced in a factory that's 1,000 times cleaner than a hospital operating room. It all begins with a wafer, a thin disk of pure silicon, a non-metallic natural element that conducts electricity. An automated container system moves the wafer through more than 800 operations. At each stop, the wafer receives one of several layers of non-conductive materials, such as silicon dioxide, and conductive materials such as copper. The machines coat the layer with light-sensitive fluid, then apply UV light through a glass stencil of the complex pattern of electrical circuitry. The exposed areas of fluid chemically react, locking the material directly underneath into the circuitry pattern. Chemical baths then remove the surrounding fluid and material, leaving only the layer of circuitry. Electrical pathways 2,000 times narrower than a human hair. A robot tests the circuitry for every memory chip on the wafer. A single wafer, measuring 12 inches in diameter, yields hundreds of memory chips. The goal is to make those chips as small as possible. In this industry, it's all about maximum memory in minimal space. That's why this operation thins the chips by grinding away 2/3 of the silicon from the back side of the wafer. And one last step before cutting the wafer into individual memory chips. This machine applies tape to hold the separated chips together. A computer-guided saw slices the chips apart. Cutting silicon is like cutting glass. It requires a diamond-edged blade. In the next step, a robotic arm, following the wafer map generated earlier, picks up the chips which pass testing and attaches each one to a fiberglass lead frame. The term lead refers to the frame's pins, which connect the chip to the digital device. Another robot wires the chip to the lead frame with gold thread that's about the width of a human hair. Gold is very conductive, so now the pathway is complete.
So I love how it's made. But, you know, when I saw this, I was struck by how similar manufacturing of semiconductors is to biology, right? They're both batch-based processes, right? As you saw in semiconductor manufacturing, you have to take the samples, the wafers, around the facility to different machines. You do one operation on one machine. Then you have to take the wafer out, the sample, to the next machine, you do the next operation, and so on. And this has so many parallels in biology. You know, we have stations, we have people that do things. And I wanted, you know, I started kind of digging into that to understand how they got there. And what was really, really interesting was that they got there by accident. So SMIF stands for Standard Mechanical Interface Format. Their automation solution didn't like arise because they were looking for how to automate the process. They were looking for a solution to the problem of wafer contamination. So in the 1980s, when as data feature sizes on microchips began to shrink, even the cleanest clean rooms were too dirty. And so their solution was the SMIF box. That's not what they call in the beginning. Basically, the box is a super clean room. So you still have the same number of particles per cubic meter that you normally have, except the SMIF box just kind of biases off. So you have the same 100 particles in the box, except now all those particles are in one small corner and the wafers are safe. And so, you know, designing that system, you know, was very successful quickly, but then they decided that they wanted to program the machines. And so their first iteration, the SMIF box, also included circuitry to set the settings on the spin coder, right? So when this box attached to the spin coding machine, it also had the settings for the RPMs and the dispense time and everything else, so that the sample itself began to carry around the instructions to these different machines. Today, you know, all that's done through networks in other way, but that path of providing a secure, safe environment that's trackable, auditable environment for your samples was where automation started, right? You solve the real problem, the sample problem, and then the automation you build off of that. And I've been thinking about how to do this in biology, and I think it does involve a community effort. In the semiconductor industry, it was you know, standards-based groups, and in other examples, giving some other examples. I think another example I find incredibly inspiring is Open Compute Project. And so for those of you not familiar with this, it's a collaborative effort among big tech companies to develop an open source alternative to proprietary rack mount servers. So on the left, you see traditional ones. On the right, you see the open source ones from the Open Compute Project. First thing you'll notice, a cosmetic difference, no bezel, right? That saves about 10 tons of plastic waste when building a single data center. And not only that, the servers also run cooler and more efficiently. And cooler means more reliable, right? The bezels just interfere with airflow, which begs the question, who decided to put bezels on servers, right? It wasn't an engineer who said this is the best decision. When users develop hardware, they end up in a very divergent outcome. And getting rid of bezels is cosmetic, with some functional side effects. More interestingly is that the architecture itself began to diverge from conventional servers. So at the time, blade servers were the trend in big IT enterprise infrastructure. And a blade server is basically a small board, the size of paperback book, say, not a stick, but about that dimensions, with the CPU and the memory on it. And those would slot into a box on your rack. And that's how you would add servers to it. What the Open Compute project has arrived at is a rack module, like one of these sleds, of nothing but CPUs. And then a separate rack module of nothing but RAM. And this is interesting and powerful capabilities because now they can create virtual servers, like a 1 gigabyte server with 2 gigs of RAM. One CPU server with 1 gig of RAM, or 4 CPU server with 8 gigs of RAM, or a 32 CPU server with 128 gigs of RAM. All of that is done dynamic configuration rather than relying on that blade architecture, which is hardwired capabilities. There's other incremental improvements they made, like switching the main supply voltage from 120 AC to 40 DC. And the list is very long. It's taken a long time to get there. But companies that have implemented this, and this was started by Facebook, it's estimated that Facebook has saved over $1 billion by switching to developing their own hardware in collaboration with other companies. Data centers that are built with Open Compute project specs cost 28% less to build and 30% less to operate, just because they're more efficient. I mean, the Open Compute project even specifies out like air conditioning, how to do the air conditioning differently. And as far as who's a part of this project, a lot of big tech companies are contributing to this. One point I wanted to hammer home here is that open source, people think of open source contributors as being individual engineers, right? The guy living at home, working in a garage or hacking away. This is especially true in the hardware space. If people think of open source as the makers and instructables, right? Amateurs. And I don't use that word in that pejorative sense of amateur, right? Like someone who's not skilled. It's somebody who's doing it. I like the Latin roots of the word amateur. Originally, the word meant one who loves doing this, an amateur, like amar, as opposed to one who's paid to do it. And so that's what I mean about it. Like most open source contributors and makers are amateurs. Open Compute, these engineers are paid to do it. Google contributes to the open source project because they get money. They save money using this technology when they build their data centers. So does Facebook, right? Open source projects among big companies drive huge changes. And so this has been a great example. Linux is another good example of that. The estimated cost of reproducing the Linux kernel today would be, I think it was $25 billion, which is insane. And that grew organically with no direct costs to anyone. And it's free and open for everybody, and everyone uses it, and it powers the modern economy. Other examples of this, successful open source hardware project, Alpha. So this is an open source camera system. All the Google Street View cars are built off of Alpha architecture, at least the cameras are, right? Google use it because it's cheaper than starting from scratch, and their contributions back into the community benefits the other people in the community, right? It's a very kind of community-centric, user-centric approach to development, lightweight innovation. Comparatus is another good example of this. It's a little much more, it's newer, project to kind of reimagine how studio production grade production equipment looks like. Right. So back to this quote. What we can do in biology, infrastructure-wise, the hardware, right? We have the technology to make something entirely different that works for everyone better than what we have today. We just have to be able to imagine that. So just some closing thoughts. And this is where I'm just going to steal right from Open Compute. This is a slide that they have on their homepage, right? Take control of your technology future, right? The Open Biotech project is reimagining hardware, right? Making it more efficient, flexible, and scalable. Join our global community of technology leaders working together to break open the black box of proprietary biotech infrastructure to achieve greater choice, customization, and cost savings, right? Why don't we have this, right? Biotech is a huge industry worth billions of dollars with companies that have hundreds of trained mechanical engineers. We can take control of our technology future, not rely on outside providers whose interest is putting plastic bezels on boxes. Rather, our focus is on getting better data more reproducibly, and more scalable. Anyway, here's my contact information. Please feel free to reach out or follow me on Twitter if you guys are interested in this project.
Thank you, Dr. Quinonez, for that informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. If we are unable to get to your question, we will follow up with you via email after the presentation. Let's get started. The first question is, where can I download copies of the designs?
Hi. So the designs right now I have on, if you're familiar with Fusion 360, it's a CAD software from Autodesk. The reason I mention that is that part of that software is the ability to share repositories of CAD data easily among users. It's a cloud-centric data storage model. So if you contact me, I will send you an invite to that repository of information. It's a little, I'll warn you, it's a little unstructured. I mean, it's like elaborate CAD data can be, and dense and hard to get through. And one of the things that we'd like to do is kind of clean it up and make it more accessible to somebody other than highly skilled engineers that spent days getting familiar with it. Yeah, please send me your contact information. I'll get you added to that, but you will need to have a copy of Fusion 360. If that software is free for anybody in academia, so if you have a .edu email address, you can get a free license as long as you have that. It's also free for startups. You'll get a 1-year license for free if you make less than $100,000 a year as a startup. And otherwise, the license is incredibly affordable. It's great CAD software. Yeah, so I'll add you to the repository so you'll have access to all that data, and certainly appreciate any help on improving the designs forward.
Thank you. The next question is, how can someone get involved in this project?
Wow, that's a good question. It's a tough one. This is a project I've been working on for a long time. I started this way back in 2009. In some of the challenges I had early on were getting people excited about this, right? Because most scientists and companies, they see this are results oriented, right? You get that information. I don't really care how it's gotten. I think the biggest thing to do to help in getting involved is just communicating to other people that there's an alternative. And certainly if you have other ideas, and, well, I mean, so there's communication, getting other people engaged and excited about this, because I think one of the big payoffs for this kind of open architecture would be the benefits to education, basic STEM, right? Because so many schools and universities don't have access to modern scientific equipment, but they may have access to a 3D printer. That would give us the ability to like easily recreate like modern equipment, right? Kids could learn the same kinds of hardware that they'd be exposed to in real industrial setting. And this is what you see at Linux, right? Like the software you learn is the same software they use in industry. You could do that for bio as well. And so if you know, you want to help volunteer to get something set up at a local school or on a project, that'd be great too. And finally, if you have any other ideas for like how to help to get involved, or you just want to stay in touch with this, I definitely appreciate that. And again, please contact me. Unfortunately, though, not as much as I'd like. You know, some of my responsibilities here, actually most of them focus around like internal enterprise development work that we're doing here to modernize our infrastructure for production of all this. But you know, there is some. There is some opportunity here at work to do some high impact contract projects. But I also know a lot of engineers that are familiar with this architecture that potentially could help out on projects. Again, it really depends on project specific and how in depth it is. You know, and for a good project that also has marketing impact, it's actually a lot easier, right? It's one thing I've learned as a director of research is that the output of research is really marketing, right? I mean, as a scientist, you're trying to market your ideas and get them, you know, push them forward, which is essentially what research is doing. So, one like good opportunities for like market, projects that have marketing impact are way more likely to get to be able to get done here at Fathom. Otherwise, I have friends. I know people can help. Yeah, please reach out.